So in the last lecture, as we discussed about sampling, do you have any doubts in that part, sampling?
Not really. It's quite clear. Maybe we'll have a brief recap about sampling because yeah, I was doing something else, other assignments, so it's like take a lot of my time. I was like,
So let's
maybe we'll have like 10 to 20 recap that we.
Yes. So just give me 1 second.
Cool.
So here we go. What we were doing was we were converting our analog signal to digital signal, right? And the method was called PCM, which pulse code modulation. PCM means pulse code modulation, right?
Yep.
And this PCM process, pulse code modulation, was this has 3 parts, basically 3 steps in PCM. What are those steps? First step is sampling, second step is quantization, and third step was encoding. So if you have to draw the diagram for PCM, it would be something like this. Here you have your analog signal, which let's say represent by x of t. This is your sampler, which will do the sampling at some sampling rate, let's say fs. This sampler will do the sampling at the rate fs, sampling rate fs, and then after we have the sampler will give you the output as xs of t, which is the sampled version of the analog signal which we gave it, right?
Yep.
Then after the sampling process will come the quantization or quantizer. Quantizer will do quantization of this signal. And we talked about quantization only in brief. So quantization was nothing but a process to convert the amplitudes into discrete levels, right?
Yep.
The continuous amplitude of the signal was to be converted into discrete levels, and that is done by the quantizer. After here, let's say I'm representing it x cube of t. Or it will not be a function of, okay, it will be. Then this quantized signal, this is known as your quantized signal. Then this quantized signal will be given to the encoder. Encoder will do encoding, and then you finally get your digital signal, which we wanted.
Yep.
And this digital signal will be in terms of the bit stream, we can say.
Yep.
Okay. Now let's revise what was the sampling process briefly. So in sampling, what we were doing, first of all, what was sampling? For example, we had this analog signal x of t versus time. So what to convert it into a sampled version, what do we need to do? We have to take samples of the signal at regular intervals. Let's say this is 0. What will we do? We take a sample after time ts. One first sample will take at 0, then at ts, then at 2 ts we'll take the sample, then we'll take at 3.
This, yes.
Like this. On this side also and on that side also. So this is what the meaning of sampling is. Basically, from the original continuous time signal, we'll take the sample on the samples and we will make the time axis discrete. In sampling process, we make the time axis discrete, right?
Yeah.
And how did we do it? Mathematically, if we want to say, so what did we do? We multiplied the signal with an impulse train, dt and del s of t. Del s of t was our impulse train. Impulse train, I told you, is nothing but impulse train with time period ts. Time period equal to the sampling interval. So this was the masses bit. So let's say this was your message signal, and here we have impulse train with time. Every impulse will be separated by a time interval of ts. So you'll have many impulses like this on both sides after every ts time. So this is ts, this is 2ts, 3ts, minus ts, minus 2ts, and so on. So now what we had to do to get the sample signal, we had to multiply in time domain the signal, the original signal, with the impulse train. And what will it give you? So for example, if you are multiplying these two, so you can see for these intervals where there is no, delta st is 0 for this, for this, for this. So for these intervals, if you will multiply it with this x of t, the multiplication will give you 0 only, right?
Yep.
So here, for all these intervals, you'll get 0, but you will get the samples only at the instance ts, 2ts, and 3ts, some values.
Yep. Yep.
What will be those values? Those values will be the values of xt at that instance, at those instances. So ts,
Yep.
2ts,
2ts,
3ts, like
ts,
that.
negative ts, negative 2ts.
Yeah. So at this 0, the sample of xt is this much, and it is multiplied with this, so it is 1, and this is the same sample we'll get here. Then the sample of ts, sample of xt at ts. So something like this at 2ts, then at 3ts.
Yep. Like
this. And similarly on the other side. And always remember, if you will join the heads of all these samples, you should get this signal back. So for example, if you join their heads, it should give you the shape of this original signal, analog signal.
Yep.
Right? So this is what? This is your sampled signal xs of t. And these intervals are ts. Like that. So now in excess of t, you have samples after every ts time. Then, and also we saw how to write this ds of t in mathematical form. So it was the summation of different shifted impulses, and n goes from -infinity to infinity, right?
Yep.
Then excess of t, also we saw the mathematical expression. It was the multiplication of these two things. So x of t multiplied with delta s of t. And when you multiplied, what did you get? X of t multiplied with summation t minus nts, and goes from -infinity to infinity. When you take it inside, it was something like x of t into delta t minus nts. And when you multiply any signal with the shifted impulse, what do you get? That signal will give you the values only at these instants. Means t will be now nts always.
Yep.
Because at all other values, it becomes 0 after multiplication. So this was the mathematical expression for your sampled signal. And we did questions also based on this result, right? This is what? This is the mathematical expression for your sample signal.
Yep.
And how to apply this in questions? What do you need? You can see here there are only two parameters. One is ts. So you should know what is the value of the sampling interval. And sampling interval you can find out using the sampling frequency. And they are related by the relation ts is equal to 1 by fs. So either one of them will be given to you. Or you have to find using the theorem which we discussed in the last class.
Yep, absolutely. Is the doubles, the sideband is the BS and all those things. The two bandwidths, the bandwidth, FM and all those things, bandwidth of the message signal, and then they just try to play around with it.
That was the minimum value, but the actual value was Fs is equal to 2 times the bandwidth plus the guard band.
Yep. Yep.
This was the way to find out the sampling frequency, and using this you can find out the sampling interval. This will be required here and here. Now, what else do we need? We need x of t. X of t will be given to you. This is our given signal. Then what will you do? You will replace t with NTS. TS you have. You will just replace it with NTS. That expression you will put here and you will multiply. This way you will get your mathematical expression. Right?
Yeah.
So this was all about the time domain of sampling. Now there was the frequency domain concept also. So for this signal, we had, this was a random signal. So let me assume the random frequency domain. Let's say it is from -b to b. This is your f. This is your x of f. Means Fourier transform of, or the frequency response of this particular signal. This is just an assumed frequency domain. Okay. But then we discussed that the frequency domain of the impulse train is also an impulse train. But this period will be Fs in that case. So it will be something impulse like this. Also 0, what? Okay, let me take it here. Impulses will be like this. This is Fs minus Fs, then there will be 2Fs.
Yep.
And minus 2Fs, something like this. This is what?
Yes.
Frequency domain of the impulse train, del S of
Yep.
F. Then frequency domain of the sampled signal or spectrum of the sampled signal, how to find out? I told you. In this case, you had to draw the original signal spectrum first. So -b, 0, b. Then what you had to do? You had to shift the spectrum by Fs on right side and on left side. So if you shift this point, it will go to Fs minus b.
Yep.
This point will go to Fs.
Fs, and then this one is b plus Fs.
Fs. Yeah. And if you shift it on the right side, you have to shift from here.
B, yeah,
B
b minus Fs and a negative Fs.
So b minus Fs, then minus Fs, and
minus
then
Fs minus b minus Fs.
So this will be your shifted on the right side, and it will go on. Again, you have to shift by Fs. Again, you have to shift by Fs. So this is the spectrum, which is Xs of F. Right?
Yep.
Now, there was this concept of guard band. This is known as the guard band. This portion is known as the guard band. Which is equal to, you can say guard band will be equal to this point minus this point. So Fs minus b minus b.
Yep.
Yeah.
So it's Fs minus 2b.
Minus 2b. Now you see,
But can I ask? Normally in the question, will they tell you the guard band, or we have to calculate the guard band? You know,
sorry, it might be anywhere. Huh? If you know the relation, no matter they ask you or they give you. Like here, there are 3 parameters. One is guard band, one is sampling frequency, other is bandwidth. Any 2 parameters they will give you, and third one you have to find out using this relation.
Well, you know, is it possible that they only give you 1 cases and then you have to find another 2 cases?
No, no,
normally...
you can't solve it.
Oh, okay.
Okay. Yeah.
Okay.
Yes, so this is your guard band. Now, based on this guard band, there were 3 cases. One was overlapping, non-overlapping, and just touching, right? So those cases were for the reconstruction purpose. So for means if we want to reconstruct our original signal back from this, means if you want to go from here to here, then what do we have to do? First of all, you should know what to do, what is to be done. So this was the whole sampling thing. Next topic is reconstruction, which we'll see. But from here, the questions were based on either on this, or it can be based on this result, or on this result, or yeah, the guard band only, means the graphs of this. The next type of problems can be based on the reconstruction. Means this was the whole sampling. What we did, we converted analog to digital. From here, we have reached here. Now the next process is coming back. From this, if you have to go back, then what is to be done? Reconstruction.
Yep.
Reconstruction of the original signal. So there, what did we need to do? We use a low pass filter for that. Low pass filter we use for that.
Low pass filter, yes.
Yes. And we apply the
Signal.
sample signal to it. Sample signal we apply XTO, XS of t, and it should give us X of t, sorry.
Yeah.
Right. So now you see, if it has to give us X, what does low pass filter do? Low pass filter does nothing but multiplies the given frequency spectrum. If the spectrum is like this, this is your Fs, 0, minus Fs, and continues. This is the spectrum of the input signal, Xs of F. Now this low pass filter will also have its own spectrum. The spectrum of the low pass filter looks like this. Let's say H of F versus F, and it will be something like, for ideal low pass filter, it will be something like this. This will be the frequency of the low pass filter, and this will be the frequency of the low pass filter. Now, what do we generally do? We take this, and this is magnitude is 1. So this we take as minus B, this we take as B. So what does this low pass filter do? It multiplies the frequency domains, or it does convolution in time domain and multiplication in frequency domain. So if it will multiply these two signals, so what will happen if it will multiply these two signals? You can see outside minus B and plus B, it is 0, right?
Yeah, because the filter, right? The filter out all the distorted, the redundant part. So they only keep the one that is low pass. So basically, outside of the filter, it's all gone. It's all dead. Only the one below the rectangular things. Yes.
Yes. So if you multiply this with this, so you can see outside from up to minus B and after plus B, all things will become 0, and it will be multiplying with 1 only this much portion. So multiplying with 1 will give you the same thing. So you will get the same result, minus B to B. So this will be the output of the low pass filter, which is our original signal XF versus F, right?
Yep.
So this was easy if this point, which is Fs minus B, is greater than F, right? This you will get if Fs minus B is greater than B. Then means we can say Fs is greater than 2B. Then we will get this thing. But what if that spectrum was something like this?
Oh, it's not very good. It's overlap, isn't it?
Yes.
This is not very good.
Minus B to B, this point is your Fs minus B. So now you can see, when you will pass it, you will get spectrum. This portion also you will get. So this and this will be mixed up. So what will happen? Overlapping is happening, and it will give you the distortion. And this case is Fs minus B less than B, means Fs is less than 2B. So if Fs is less than 2B, then overlapping will happen, and you won't be able to reconstruct the signal back. But if Fs is greater than 2B, it will be no overlapping, and you will be able to easily reconstruct your signal back using the low pass filter. right? And it is greater than, but how much greater than it will be? The actual relation is this, Fs plus the guard band.
Yep.
You can see, if you write only 2b, if you can say guard band, there is no guard band. Guard band is 0, then it will become 2b.
B.
Right? If it is greater than 0, it will become 2b plus something, means greater than 2b. If it is negative, negative means they are overlapping, then it will become less than 2b. Okay?
You're correct.
Then we defined a term called Nyquist rate. Nyquist rate was nothing but the minimum sampling rate required for reconstruction.
Yep.
It was Fs minimum value of Fs, which is equal to twice of the bandwidth of the original signal. Right?
Yep.
Then after this, we also have a Nyquist sampling theorem. Nyquist sampling theorem. What it is also this, it also says the same thing. It says that if B is the bandwidth of your original signal, then you need to sample the signal at minimum Nyquist rate to reconstruct the signal back. Means Fs should be greater than or equal to 2 times of B. Nyquist theorem is nothing but this only. Okay.
Yep. Yep.
So this was all these were all the things which were discussed in the last class.
Okay, so let's continue. Let's continue with the quantization encoding. Maybe we do.
Part.
Yeah. Yeah, I think we can continue with that. I just want to finish the lab sheet and all those things. Yeah. So I think let's just finish the pre-lab question. But the pre-lab question,
we'll be able to finish that only after learning the concept, no? So first,
yeah. So we stick with the concept and then we go back to the pre-lab sheet. Yes.
Yes. Okay. So quantization. What is the quantization method process? See, in quantization, let's say this is your quantizer. And the input to the quantizer is, let's say, we denote it by x of n. This is the sampled signal x of n. Then the output of the quantizer will be denoted by q of n. Sorry, y of n, which is denoted by q of x of n. Q of x of n means quantized version of xn. Quantized signal xn. Then, now see, what does this quantizer do? So for explaining that, let me draw a diagram.
Sure. Do it slow enough. Do it. Make me understand. Yeah, that's the most important part.
Yeah. So, for example, if your actual signal is something like this. This is your signal, okay? Now, you see one thing. What is the minimum and maximum value? This is x min. And this is the maximum value of the signal, x max. Right? What will we do now? What does the quantizer do? It breaks this. First of all, it draws some boundaries for the signal, which are equally spaced. What do I mean by boundaries? See. So the first decision, and we call them decision boundaries. So first boundary will be at the minimum, D1. Then after some gap, there will be another boundary, let's say D2. Another boundary, let's say D3, another boundary, let's say D4, and the final boundary here, let's say D5. So there are 5 decision boundaries. D5. These are your decision boundaries. And then what do? You have to find out the midpoint of all these decision boundaries. Midpoint of all these decision boundaries.
Okay.
So you see, the midpoint of these two decision boundaries will lie somewhere here. Then these decision boundaries somewhere here. Then for these two, this will be the line which is the midpoint. For these two, this is the line which is the midpoint, right?
Wait, I'm taking this down. Okay, T5. Okay, so the midpoint. Okay, so you talk about the midpoint between the. Okay.
Midpoint.
Midpoint. Okay. Midpoint. Yep. Okay. Understood. Okay. Why midpoint is being used?
Yeah, I'm explaining that. Just have some patience. So these midpoints, these lines which we draw, which passes through the midpoints, they are known as quantization levels.
Can I know the meaning of quantization? I'm a little bit confused with the literal meaning, quantization.
Quantization means converting the amplitude, which is continuous in nature, into discrete levels. For example,
wait. Convert the amplitude, which is analog in nature.
Yes, which is analog in nature to discrete in nature. Amplitude. For example, you had this signal where these sample values can be anything in the range from 0 to 5, for example. Can take any value, can take 3.5, can take 4.78, means any value, real. The magnitude of x of t belongs to the real numbers, right? The number of values it can take is infinite. Okay, there are so many values. But now what we want to do, we don't want to take the amplitude any value it wants. We want to force it to take only a particular set of values. Means any values out of that set it can take, outside that set it cannot. For example, we can bound it that it has to take only the values 2, 4, 6, 8, and 10. Outside this, it cannot take any values. So this is quantization. Here, it was continuous in nature. Magnitude was continuous in nature. Here, it is discretized. Right?
Okay. Discrete,
so
yes.
This process from going here to here is known as quantization.
Okay.
Understood? And actually, how it is done, now that I'll show you here. So quantization level, sorry, this is your level 1, this is level 2, this is level 3, and this is level 4. What are these levels? These values are the levels. Level 1, level 2, level 3, level 4, level 5. Okay? Yeah. So these are the levels. Now, basically what we are doing, the whole range, which is from x minimum to x maximum, this whole range we have to map onto these 4 levels. Are you getting my point? See how?
Oh, okay. I have some idea. I think it's like a cutoff, isn't it? So it's like pia, 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 pia. So it's a specific discrete. Can I think it like this way? It's like cutoff. It's like, okay, I want this precise value.
See, it will be very clear once I'll finish this thing. Let me finish. See, for example, here, the whole values, the values which lie, the signal which lies between D1 to D2, it has different values in the range D1 to D2, right?
Yep.
So let me show you here. Let's say this is your 0. This is your 2. This is 4. This is 6. This is, can be anything. Let's say 8. Now you see, this value will be 1, right?
Yep.
So if the signal takes any value, if let's say the signal value over here is 0.2, for example, this is 0.2 on the vertical axis, this is 0.2, for example. We will map that to 1. We will map this 0.2 to 1. Means anything which lies between these two boundaries will be mapped to the midpoint.
Yep.
If the signal here is 1.9, we will map it to again 1. Instead of taking 0.9, we'll take 1. Instead of taking 0.2, we'll take 2. So that means any value of the signal which lies between these two decision boundaries will be mapped to this 1. Any value which is between 0 to 2 will be mapped to 1. Got it?
So can I ask? So if it's 0.2, it will be 1. If it's 1.8, it will be 1 as well, is it? Or I'm wrong?
Sorry?
If it's 0.2, is it 0 or 1? 0.2 is different.
1.
1.
How
about 1.8?
It is also 1.
Why it's not 2 now? Because
that's the way it is defined. No? That's how we are defining it. See, by common sense, what you are doing is you are saying, okay, 0.2 is closer to 0, we should map it to 0. 1.8 is closer to 2, we should map it to 2. But no, that is not quantization. No? Quantization is the process which we are defining. Not like this, we are defining it the way that we'll have some specific levels and we want to map the whole signal to those levels only. So we have the level, either we will have the level L1 or we'll have L2 or we'll have L3 or we'll have L4. So all the values we have to map only to these 4 values. Okay. So you can say 2 is not in the options. Right? So you can either map it to L1 or to L2. So now you can say it is closer to L1. That's why we are mapping it to L1.
Understood.
Yeah. So that means all the points which are lying from D1 to D2 are closer to L1. So we will map them to L1. So this point to L1, this point to L1, this point to L1, this point to L1, this point also to L1.
Yeah.
So let me use a different color. Okay, let me draw the separate graph for the output. This was the input. Okay, let me draw it here only. So from here to up to this point, the value will be, all these values will be mapped to 1. So can I write it like this? Can I draw it like this?
Yes.
Then, after this level, means after horizontally we have crossed this level, to D2 to D3, it falls up to here, horizontally. So from here to here, all the values will be mapped to this L2, like this.
Okay, understood. So basically, let's say I'm 3.2, it will be 3. 3.8 will be 3. If it's 2.2, it will be 3 as well, I assume.
Yes.
2.2.
Yes, that's what I'm saying. Yes. So then from here to the D4 level, which is on the horizontal axis over here. So
but can I ask why does it have to follow the quantization level? You know, that's the point. It's very weird, you know, it's very fishy, you know. It's like 0.2, 1, not 0. You still have to finish the quantization length. But you know, this is sometimes, you know, you just like, why is that? You know, it's not very rigorous, you know. It's like, if I know if it's more than, you know, if more than a level, then it's probably just follow the L2 because you haven't reached L4. But you're below, you also have to follow the, you know, quantization level. It's just very weird. For me, 0.2 to 1 is just very weird. I'm sorry, it's just very weird.
Yeah, okay. Let me clear that point. See, this is the very basic one, basic quantization, which we do. But after that, like, there are improvements to it, like adaptive quantization. Okay. In adaptive quantization, in this case, this was the very first, like, you know, very basic type of quantization. In adaptive quantization, the quantization levels will be adjusted as per the signal variation. Okay. In this case, obviously, like, we'll study about one term known as quantization error. We'll study about quantization error. So what you are saying will be covered in this topic. Means,
okay,
it will tell you that okay, we can map the signal like this, but there will be a huge quantization error which we need to minimize. So there will be some methods to minimize the quantization level that we'll see, but for the time being, you just understand the process. Okay, how it is done.
Understood.
Yeah. So from here to here, it will be mapped to the midpoint, mid boundary, means level L3. Then level 4. up to this level is level 4. Level D4 to D5 will be mapped to the mid boundary.
Yeah.
Then again, you can see it is coming here. So up to here, it is falling D5 to D4 boundary. So again, it will be mapped here only. So you can see we can join them like this. So the input given to the quantizer was this. This was the input given to the quantizer, and the output which the quantizer will give you is this black one. Staircase waveform. Something like this. Something like this, which we just saw here, right? And these levels are what? Now, okay, let me see here. This was time axis, this was your amplitude axis, x of t. Now this is your time axis, this is your amplitude axis, x cube of t. You can see this value was our L1, this value was L2, this value was L3, this value was L4. You can see on amplitude axis how many values it can take. Only 4 values. Even further also, if you'll do it, it might look something like this. But it will take the amplitude out of the 4 given levels only. It might be something like this, but it will be taking only level 1, 2, 3, 4. Amplitude cannot be anything in between. It will be
ask why the shape is like this. I'm a little bit confused with why the shape is. Can you just?
Here, you just drew it. No, we just drew it here. You can see this shape.
Oh, so it starts with that and then go up and then okay, this is shape. So the basically is follow the L2, L1, L3. Oh, okay. It's following the shape.
It's following the shape only because we are bounding it to take only 4 specific levels. So either it will go directly up, it will go directly down, directly up, directly down. It has no other choice to move in other phase, right?
Yep, understood.
Yeah, so this is the process of quantization. But now the problem comes the quantization error. So if I just take an example and explain you, for example, our original signal x of t was taking the values. Well, it can take any values, but just for example, I'm giving you that 2.4, 2.5, 0.5, 0.78, 3.5, 3.8, 4.9, 5.6. Like these are just some of the values. Then quantization signal will have for all the values which falls between 0 to 2, it will map it to 1. So it will make it 1. This is also 1. This is also 1. This is also 1. This will be 2. This will be taken as 2, taken as 2 or 3. 2 to 4 was taken as 3. Oh, sorry, 3.
Yeah, I was like confused. And I was like 3, right? I was like, I didn't interrupt you. Yeah, 3.
Yeah.
4.
2 to 4. This will be 5.
This one 4, right?
4 to 6 was 5.
Or 5.
4 to 6 was 5. So you can see there is a huge error. So how much is that error is known as the quantization error. What is quantization error? Quantization error is the difference between this original sampled signal and the original amplitude and the quantized amplitude. So here the error is 1.3 plus or minus 1.3.
Oh, minus, okay.
And here the error is
minus 1.4.
1.4 minus 0.5 minus something minus like this. So the error can be either positive or negative, right?
Okay.
And what can be the maximum? Okay. For that, let me just tell you what is the difference between 2 quantization levels and 2 decision boundaries. This we denote by delta. And it is same between the decision boundaries and the quantization levels. Let me denote it here. I'm defining a term called step size, which is delta. It is what? It is the difference between two quantization levels, two continuous or consecutive quantization levels. Or between two consecutive decision boundaries. It is the same thing only.
Yeah.
So I can write it as L2 minus L1 or L3 minus L2 or L4 minus L3, anything will be fine.
Yep.
So this is the step size. Now, once we have defined the step size, also, first of all, number of why? Let me answer this question of yours. Why are we doing this? Why are we converting it to quantization levels? So here was our method.
I think you want to make it you want to make it to discrete in nature, isn't it? You want to based on analog, because analog is continuous, which is not good.
Yes.
You want to make it to digital, so discrete.
So encoder, here we need to first, here we need to have bit streams like 0, 1, 0, 1, 1, 1, 0, something like this. So how the encoder will do that? Here what we are doing, the before step is there will be only some fixed levels like 2, 4, 6, 8, something like this. So how many total levels are there? 5, 4, 1, 2, 3, 4. So we want to represent these levels into bits, right? So means there are 4 values. These 4 values can be represented by 2 bits. So for example, we can just encode it as 0, 0, this as 0, 1, this as 1, 0, and this is 1, 1.
Yep.
So basically encoder now have only 4 values to convert into the bits. So it will convert, if anytime it gets 4, it will send 1, 0, 0, 1. Anytime it gets 6, it will send 1, 0. Anytime it gets 8, it will send 1, 1. So this way we are converting it to bit stream, right?
Yep.
And if you can see, if you will have more number of levels here, you will need more number of bits to represent. Let me write it over. More number of quantization levels implies more number of bits will be needed to encode. Have you studied digital electronics?
Yes, I've studied digital electronics. Yes.
Okay, very good. So if you have, let's say, using 2 bits.
Yes. Okay.
Using 2 bits, how many numbers can be represented?
4, right?
4 numbers.
Yeah.
Using 3 bits, 8 numbers can be.
8, yeah.
Using 4 bits, 2 power 4.
16.
This way.
Yep.
Means more the number. Here now these are your levels. For example, if you have 7, 8 quantization levels, L1, L2, L3, L4, L5, L6, L8. So to represent these 8 levels, you will need 3 bits.
Okay.
If you have 4 levels, you will need 4 bits. Like that, right?
Okay.
So that means if we have the n-bit encoder with us, if we have an n-bit encoder that is predefined, how many bit, like encoder is how many bits. So using that encoder, accordingly you have to convert, accordingly the quantizer has to, function. So the number of levels here should be 2 power n. Only then this encoder will be able to encode all of the quantization levels, right?
Yep.
So that means here we have to first of all know how many levels we can represent the signal with. So here let me mark it. If we have n-bit encoder, then the number
I'm sorry. I have to go to the washroom. We'll be back very quick.
No problem. Go.
I'm back. Yeah. Hello.
Yeah.
Continue.
Yes, yes. See. Now, this is what I was telling you that we'll have this. So that means always whenever we discuss about quantizer, so quantizer will, the number of quantization level will always be a power of 2. Means it can be 2, 4, 8, 16, 32, 64, like this whole.
But yeah, yes.
We will select it that way. Okay, most of the times. Understood?
Yep. Yep.
Yeah. So after this, where were we? Okay, this was the step size. But now you have to see one thing. If you want to, okay, step size, how to find out the step size mathematically? So step size delta is what? See it from the diagram. Here we had the range from x minimum to x maximum. And we were dividing this range into how many intervals?
Yeah.
How many equal partitions we are doing for this range?
Okay, 4, right?
4, right? Which is what? Number of levels? Right?
Oh, number of levels. Yes.
Number of levels. So basically, and all the partitions are equal. So that means if this is your delta, this is delta, this is also delta, and this is also delta. So this whole range from x max to x minimum, can I write as 4 times delta? X max minus x minimum as 4 times delta. Where this 4 is what? The number of quantization levels. If I want to generalize it, it will be 2 power n.
Yeah.
And if you take 2 power n in the denominator, can I take it like this?
Oh, we can do that. Yes.
So that means we found the general formula for delta. It is the range amplitude range divided by number of levels.
Yep.
So let me write it here. It is the range, amplitude range, x max minus x min divided by number of quantization levels. Very important formula. Or x max minus x min by L, where L denotes the number of quantization levels. Right?
Yep.
Now from this, you can see, if you have a signal, if you are given a signal, then obviously its range will be fixed, right?
Yep.
Amplitude range will be fixed. We can't do much about that. So, but if I'm telling if x max minus x min is fixed, then can I say delta will be inversely proportional to the number of levels?
Yep. Yep.
Then more the number of levels will be, obviously the gap will reduce, right? For example, in the previous case only, if this was the range, if you increase the number of levels, we had 4 levels. After 4, we can take 8 levels. So the this will be, you can see 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7, 8. Like this. The quantization levels will be the bound. These are decision boundaries. Quantization levels will be the mid boundaries. Like this. This is your level 1. Level 2. Level 3. Like this. Right?
Yep.
Now, there is a trade-off now. See. Can you see any improvement between the previous case and in this case? What is the improvement?
It's I don't see any improvement. I just see the range is getting bigger and bigger, isn't it? That's the only improvement I see.
Sorry?
I don't see any improvement. I'm sorry, I can't see any improvement. I just see there's more midpoint, there's it's maybe smoother.
No, the error is reduced now. Error is reduced now.
Oh, really? Error is reduced.
Yes. How? You can see that. Let's say initially this was our 0. And if it was going from 0 to somewhere, obviously you can see it from here. See. Initially, it was 0 to 8. I think 0 to 4. 0 to 8, we were dividing into how, like this whole range, 0 to 1 was mapped to 1. Now, this 0 to 8 is divided in 1, 2, 3, 4. Instead of 8, now, this is divided, instead of 4 parts, now it is divided into 8 parts. So what will happen due to this? 0, 8, 1, 2, 3, 4, 5, 6, 7. Okay, let it be here. It is 8.
Okay.
So it is 0, 4, 6, 8. Oh, sorry.
No, don't do that.
Sorry. 1 to 8, no?
Yeah.
So 1, 2, 3, 4, 5, 6, 7, 8. These are your 8 decision boundaries. Now you can see what will happen. The level will be the midpoint, this 0.5. This is 1.5. So basically what will happen now, 0 to 1 will be mapped to 0.5.
Yeah.
1 to 2 will be mapped to 1.5. Is the error is reduced now, right? Yep. Initially, 0 was mapped, 2 was mapped to 1. So the error was, if the sample is 2, it will be mapped to 1, right? So the error is 1. Now, maximum 1 will be mapped to 0.5. Error is 0.5. So the error is reduced now.
Yep.
Right? So this is the benefit of having more number of levels. Quantization error will reduce.
Yep.
More the number of levels, number of quantization levels means lesser the quantization error. But the problem is this step. Okay, the problem is the number of bits. More the number of levels, more the bits. Yep. More number of levels, which is 2 power n, implies more number of bits, which is n, are required to encode them. Sorry. Right? And you can see if the number of bits are increased now, that means you will need more storage and more capacity to transmit them. Right?
Yep.
So basically, we need to make a trade-off between them. Means we need to make compromise. If we want the error to be less, then we need to have more. And we don't have any limit on the number of bits, then we'll use more number of quantization levels. But if we have limited number of bits only, but we can compromise with the accuracy, then we'll have less number of levels, and obviously the error will be more.
Yep.
So this way we have to make compromise. And this way, the error thing which you were saying, the error can be reduced to even it can be made very negligible. If you use so many, like if you use the number of levels to be more. But again, the thing is the storage and the number of bits. Right?
Yep.
So this was the process of quantization. Here, the important terms are the step size is important. And quantization, okay, what can be the maximum and minimum value of the quantization error? Quantization.
One over number of the levels, so it's x max minus xn.
X max minus x min by 2. Delta by minus delta by 2 to delta by 2. Maximum quantization level, maximum quantization error can be half of the step size and minimum minus half of the this step size.
Okay.
So these things are important here.
Okay.
Is everything understood?
Yes, yes. I'm
Okay,
just
so
trying to
this
follow. Yes.
this
So okay,
was
increase the quantization level means more precision. Okay, more accurate.
yes.
Reduce error. Yes.
Just
Okay.
revise it once from here. Just take 2 minutes to revise it. Then we'll do a question which is there in your lab sheet.
Yeah. Yeah. Sure. Hi, can we continue? Or it's
Yes.
yeah, can we continue? Yeah. I
Yeah.
think we can start with the lab question. Yeah.
Okay. Now see. Let me just take an example.
Okay.
So you are given a signal, let's say x of t, which is equal to 4 cos 10 t. This is your xt, and you have a let's say you have 2-bit quantizer, not 2, let's say 8-bit quantizer. And you want to convert, you first do the sampling of the signal. Okay. You first do the sampling, then you do the quantization, and then you do the encoding. Then first question is, find how many number of levels the quantizer will use. Number of bits required to encode the signal. It will, sorry, take it as 4-bit quantizer. 8-bit will be too much. Take it as
No,
4-bit
no, it's okay.
quantizer.
It's okay. Well, let me think. 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 1, 2, 3, 4, 1. Is it like 7?
7 is what?
7 quantization level? Is it? Am I correct or is wrong?
No. 8-bit quantizer.
Yes.
For quantizer should not be described as bit, by the way. It should be described by number of levels. Yeah?
Yeah, seven levels, or 7 or 8 levels, maybe 7. I
No.
think it's 7 levels. I
No.
know.
No. Wait. Here in the question you are given the encoder to be used is a 4-bit encoder.
Yep.
Now do it. Number of levels the quantizer will use, number of bits required to encode, and draw the quantization diagram. Find the step size. Of the quantizer. Next is find the range of quantization error. Just try to answer, otherwise I'll help you. Also, you can find out using minimum sampling rate. Before the quantization, at what minimum sampling rate the signal should be sampled. So here xt is applied. It will go through sampling and then quantization. Just give it a try.
Can you guide me through this? I think I need more guidance. I think the number of level is 8. Oh, I'm wrong.
No. I told you it depends on the number of bits to be encoded. So number of bits to be encoded is n. Number of levels is 2 power n.
No, so it's 3. 3.
2 power n. So 2 power 4. It will be 16 number of levels.
Well, it's 8-bit, isn't it?
Okay, here I made the change because otherwise we'll not be able to draw the diagram. It will be too big. That's why I changed it to 4. If it is 8, then it will be simply 2 power 8 and you can calculate.
Yep. Okay.
Okay. Then number of bits required to encode, simply it is given to you 4 bits, so it is simply 4. Draw the quantizer, we'll come to this, then find the step size of the quantizer. Step size, we just saw the formula. It was the amplitude range divided by number of levels. So x max minus x min divided by the number of levels, which is 16 in this case. And what is the range of the signal?
From 8 to 0, isn't it? I know. From 8 to 0.
Here you see?
4.
No. Minimum to maximum. How the cos signal go? It goes like this.
Yes.
-4 to +4.
Oh, okay. All right. Okay.
So it is 4 up, 4 down, so 8.
Oh, 16, so half.
So it will be 0.5.
Yeah.
So this is done. Then range of quantization error. Quantization error, I told you, lies in the range from -delta by 2 to delta by 2.
Yep.
So it will be this divided by 2. So -0.25 to 0.25. This is the range of quantization error. Then minimum sampling rate. How did we find minimum sampling rate?
Minimum sampling rate is FS, isn't it?
FS.
Yeah. FS. And FS is 2 FM, so it's 1 over TS. So time.
Yeah, 2 times FM. And FM will be, this is, how much is FM? Here omega, this is omega t, cos omega t. So omega is given to you as omega m is 10. So FM will be, omega m is 2 pi FM. So FM will be 10 over 2 pi.
Yep.
So this is 10 by pi hertz.
Yep. 2 pi hertz. Yes, absolutely. 3 something, isn't it? 3 something, 3.14. 3. Yeah, 3.2 something.
Got it?
Yep, got it.
Then quantization diagram, how to draw. See that first. So if our range is between -4 to 4, magnitude ranges from -4 to 4, and always remember number of decision boundaries will be one more than the number of levels. Number of decision boundaries is 2 power n plus 1. Number of levels plus 1. So if we have 4 number of levels, if we have 16 levels, there will be 17 number of boundaries.
Yep.
So first boundary is this, second boundary is this, 2 boundaries, and you have to draw 15 more boundaries in between. So they will be very close, so I'll not be able to draw all of them here. So, but this is just, I'm giving a random example. So let's say they are 15. Then what you have to do, you have to draw the quantization levels. Right? So quantization levels, how to draw? Quantization level will be simply the midway.
Midway.
And then level 1, 2, level 16 you will draw. And then all the range which falls, let's say if it is like this, if your cos signal is like this, then what will you do? You will map in between. Let's say this was your 2 boundaries, right? So the signal from here to here will be, between 2 boundaries we have to see. No? So this is one boundary, this is another boundary. It will be mapped to between at this level. So the signal which lies between these two levels will be mapped to the in between. So this signal which lies between these two boundaries will be mapped to this. So you can see. So here to here will be mapped to this level. So it will be this. Here to here. Okay, this again goes upwards. So it will be mapped to the between over here like this. So here like this. Then up to here it is mapped there. But now from here to this boundary, it will be mapped to the middle. Yep. Like this. So this way the staircase waveform you can draw.
Oh, okay.
From
But it should be quite accurate. Huh? We are not very accurate here. We're not very precise here. You know, it's
yeah. I'm just drawing roughly.
Yeah, because roughly, yeah. Because it should be, if you want to be very detailed, then it can be very complicated. You know, yes. It can be step
we
function.
Just have to understand the process, and we have to draw it just roughly.
Yeah, roughly. Yeah, I think in the final exam or test, it will be something similar. You know, draw a rough graph as long as the shape is okay. I think we won't lost our marks. Yeah. Yeah.
It won't be up to the scale. You just have to explain the process. That's it.
Okay.
Yeah. So this process is clear.
Yep.
All these things. Now see the question in your lab sheet. There is only one question based on quantization. See. Question number 2. Do you have the paper with you?
I do have the paper with me. Yes. Okay. Do you want to share the screen, or is I see 4 bits.
Yeah, they are saying it is a uniform 4-bit quantizer.
Yep. Are we going to follow the question? Oh no, it's independent. Okay.
Sorry?
No, it's independent from the question. Yeah. I saw it's dependent. Okay. No, that's okay. Discrete. Yeah. Continue.
So 4-bit quantizer, it is. Then draw a diagram showing the amplitude quantization levels and corresponding binary numbers used to encode them. So number of levels, first of all, you should know how many number of levels will be there.
4.
Number of levels would be?
Oh, sorry. 4. 8.
4 to
2 to the power 4. 2 to the power 4. Yeah, 2 to the power 16.
16 levels would be there. Then diagram you have to just draw like this only. Similar diagram. And then the corresponding binary numbers to use to encode them. So this one you give a thought.
Is it based on the 4 bits? You know, is it 0 to 0 or 0, like 4 bits, right? So it's like 0 to 0 to 111. Is it like the ranges between that, or you can play around with that? Or I'm wrong? It's like digital electronics.
0 0 0 to F. Sorry, 0 0 0 number of levels. It's simply like how to encode 16 numbers. 0 to 15. If you have to encode how many bits?
Yep. You're right.
Yeah.
1 to 16 or 0 to 15. Yes. 0 to 15. Yes.
Yes. So it would be like 0 0.
But how to show the corresponding binary numbers? You know, that's the tricky part.
Yeah, I'll tell you. Just wait for a second. Corresponding is nothing but the number of levels, let's say L1, L2, L3, L4. You are mapping them like this, now L1, L2, L3, L4, like this. So this L1 will be represented by 0, 0, 0, 0, L2 by 0, 0, 0, 1, L3 by 0, 0, 1, 0, like this.
Oh, okay.
Simple.
Okay.
So L16 will be represented by 1, 1, 1, 1. We are just encoding them like this.
Oh, okay.
This is our encoding scheme.
Okay.
Everything is clear so far?
So for the diagram, I have to draw based on that. I move up a little bit. The diagram, I have to draw the things very accurately, very precise. So it's like circle going down in the middle point and to go
Actually,
down.
in this question, I'm not very sure the diagram for the diagram. They want to draw the diagram for the question number 1 xt or just any example you can take. Because maybe they are asking you to draw the diagram, quantized version of xt, which is given in the question number 1.
Yeah. How to draw that, that's the thing.
This for that signal only, I think they are asking you.
Yeah.
So for that signal, what you have to do is find just the range and quantization levels. Okay, wait.
It's cosine 3 pi times 10 to the 3 and then plus cosine 4 pi times 10 to the 3.
Yes. So for that, I don't think it will be related to that, because if it is related to that, then it will be difficult for you. Then you can just show the output of the quantizer.
I think he wants something like that, yeah. The pre-level question, it worth some marks, but it's kind of important. So it's like we can go through this maybe.
Yeah.
Like the graph. Can I Google, Google the graph?
Yeah.
I just like.
Let me tell you, it will be a cosine function only, but with a different frequency.
Yes, different frequency. You're correct.
Right? Because you can see. That's
Omega
why I'm
is
saying
different.
It will be a little bit different. See, cos of 4 pi into 10 power 3 times t. So at t is equal to 0, cos is this function x of t is 1 plus 1, 2. Right? You can just search the graph of cos omega 1t plus cos omega 2t.
Yes. Okay.
Okay. Or you can say, let's say this is your omega. You can assume cos 3 omega t plus cos 4 omega t.
Yep.
You can just search the graph of this. Okay. And the graph you just have to, once you have the graph, just plot that graph. Something like, let's say the graph looks something like this. Actual shape, I don't know what it will look like. But then what you have to do, you have to divide the whole range from its minimum. If let's say the minimum can come downwards also, let's say like this. Then what to do? You have to just first range it, the minimum value to maximum value, like this.
Okay.
And maximum value. This is the whole range. Then in between, these are two boundaries already, D1 and the D17 boundary. In between, how many boundaries? Equally spaced boundaries, you have to draw 15 boundaries.
Yes.
Like
D2,
this.
D3.
In between, 15 boundaries you have to draw.
D5, D6. So D1 to D16, right? Not D1 to D17. You made a mistake.
Boundaries. Number of boundaries will be 17. I told you.
Plus 1. Plus
yeah,
1. Oh, plus 1. Okay.
So then D1, D2, what you have to do then? Between D1 and D2, there will be one quantization level.
Yep.
So the graph values which are falling between D1 and D2, let's say from here to here, these values are between D1 and D2. You have to map it to that level, like this.
Yep. Oh, okay. Understood. I'll try to
and
follow
the values
this, yes.
which are falling between D2 to D3, let's say from here, D1 to D3. Just you can make it easy, you just draw these two lines like this and see where this graph is falling between two boundaries. Just map that to the mid. So from here to here it is falling. So map it to mid. From here to here also it is falling between this. So map it to the midpoint like this. Got it? Similarly, you have to repeat it. So that will be a quantized diagram.
Can I ask, but for D1, they will never reach D1, huh? You might never reach D1, or it's or you will touch D1 because you're not touching D1. Did you make a mistake?
You won't be able to touch D1 because it is level 1. Level 1, It is started from level 1 and D1 is
Okay.
always less than level 1. So it won't be
So,
able.
but you never touch D17 as well because it's the
No.
top one, the
No.
L. Okay, level, yeah,
Touch
okay.
means what? Touch means what? The graph will touch. The graph will touch these boundaries. I'm saying the levels will not touch, or the output graph will also not touch.
Okay, okay,
Okay.
okay.
Yeah.
Got it, got it.
Okay.
There's a lot of taking, so sometimes you get a little bit, confused, but yeah, I just need to ask.
Yeah,
Yeah.
actually, there are so many things, so syncing all of them at once is a bit difficult. Okay, the question number 2 is done. Now comes the question number 3, which is the third step, encoding, right? So, do you want to do it today only? The encoding part also? Or should we practice one more problem on quantization? Because I think it will be too much for today.
I think what we need to do is we practice another problem and then we continue tomorrow with the power spectral density.
Hmm.
Yeah, we'll do that. Yeah, we'll do that. This part we'll leave it to tomorrow.
We can take more example
Yeah, we do more example. Yes, we do more example.
on quantization, right?
Yes, yes. And then maybe we end this session early today. If we like, let's say after the example, everything goes well, we end this session early, and then tomorrow maybe we do a little longer session. But yeah,
Okay,
we'll
no
do that.
problem. So today we will end it 15 minutes early, and tomorrow we'll extend it. Okay. So
Yeah.
in the 10 minutes, we can do one more question.
Yeah, 10, 15 minutes. We'll see. Yeah, let's go.
Yeah. So just let me take. Maybe we can mix sampling, a question with sampling and quantization.
Yeah. We can do that. Yeah.
Yeah. So we have just leave this. Okay, here we have a question. Can you give me just 2 minutes?
Pardon?
Just 2 minutes, okay?
Have a break, is it? Hello. Do you want a break for 2 minutes? Sure.
Sorry?
Do you want a break or what? The 2 minutes?
No,
What do you mean
just
by
2 minutes. Let me find some question where you can
sure.
combine sampling and quantization.
Sure. Understood.
Okay. So first, let me take a question based on sampling, maybe. Consider the signal xt is equal to ten times cos 6 pi t then find the Nyquist rate. Second, find out the sampling frequency if a guard band of 400, 200 hertz is used. Third question, number of bits required to encode the signal if a 128 levels quantizer is used. Find the step size of the quantizer. And also find the maximum quantization, maximum possible quantization error. And next question is draw the quantization diagram. Draw the sample signal also, okay? Draw the sample signal and the quantized signal. If you are able to do all these questions, then it's the concepts are clear.
Hello, the question is that, I believe. Hello.
Yes?
Yes, this is the question. So the request rate and request rate.
Give it a
Request
try.
rate. Yeah. Request rate. Can we start? I think I have the sampling rate.
Yes.
So is this 3?
3 is what?
3 is the Nyquist rate. Oh no,
3
is
is
it yes, 3 is the frequency, isn't it?
FM is 3 hertz.
Yes.
Okay. Then what will
Yep.
be Nyquist rate?
2 FM, so 6.
6 hertz.
Yep.
And what will be the sampling frequency if a guard band of this is used?
Let me think. So it will be 12, isn't it? So it's 2 times 6, 12 plus 200, so 212.
Wait. 2 times B, not 2 times Nyquist rate. 2B is the Nyquist rate.
Oh, 2B. So it's a 6, 206.
Very good.
So it's 2 times 3. Yes.
Okay. Next.
Number of bits required to encode. Is it 7 bits?
Required to encode 7 bits. Okay, very good. Yes. So how did you find that?
Times 10 power 2 times 10 to the power 7.
2 power 7 is 128. So N is 7. Very good. Okay, then fourth.
Is it step size is 8, 7 plus 1, or I'm wrong?
7. No. Step size was not that, no? Step size was the range divided by number of levels.
No.
X max might. Okay, let me show you. What was the step size?
Oh yeah. So it's so can we yeah. So it's I get what you're saying. Okay. I need to see the is it 10? Is it amplitude? What is the amplitude?
10.
The amplitude is 10. So 10 plus 10, 10 plus negative 10 minus negative 10 divided by 7.
Yes. No, not 7. Okay. No, not 7. 10 plus 10, 20 divided by number of levels. Number of bits are 7. Number of levels are not 7. Number of levels you just found. 2 power 7 is number of levels, na? 128 levels.
Oh, okay. Oh shoot. Okay.
Okay, so this is
So
your step size.
okay.
Then maximum possible quantization error.
So it's that one's divided by 2, right?
Yeah.
This a range, right? It's -2 and then +2. Yeah. 2 parts.
Maximum they are asking you, so maximum is delta by 2.
Yes.
So it will be 10 by 128. Whatever the value
Yep.
is, you can calculate.
5
Then
over
the main
5 over 64.
Yeah, 5 over 64.
Yep.
Then you have to draw the sampled signal and the quantized signal.
Okay.
Sample signal, if it is sampled at Nyquist rate, because you have to tell na at what sampling frequency it is sampled. So it is sampled at Nyquist rate. So draw the sample signal in time domain as well as in frequency domain. Means the spectrum also you have to draw for the sample signal. Try to draw it and send me a picture.
Draw the sample signals and yes, okay. Frequency is how much? Frequency is 3. So it's wait, I'll try. Let me think.
Yes.
Is this the graph I sent to you right now?
Okay, let me check.
Yeah.
Okay, so what was 3?
3, yeah.
No. This is not how it is drawn.
Really?
First of all, you have to see the amplitude levels. They all will not be same. Amplitude levels will be different. Amplitudes will be different, and the time gap is also not correct. Time gap in
Okay.
time domain should be equal to TS, which is the sampling interval.
The interval is 3, isn't it?
No, why 3? Nyquist rate is 6. Means Fs is 6 in this case.
Oh, yeah. Okay. Mistake. Okay.
Yeah. So find out the sampling interval first.
So sampling interval is 6. I assume it's 6.
No.
So
it is TS, 1 by Fs, I told you.
Oh, yeah. Oh, okay.
Yeah.
Mistake. We learn from mistake, you know? Now we make mistakes.
Yeah, this is why actually, this is why it's important to do the things by yourself, because when you see it on the screen, you understand it, but when you apply, you do mistakes, and then you know, okay, what not to do.
Yep.
Yeah.
Something like this.
Consider the amplitude levels also, okay?
Yeah. -10, isn't it?
Not only -10 and 10, it will change between -10 and 10.
Yeah. So I did.
Yes.
There's a variation.
Variation as per the cosine function.
So what's how to draw a perfect one? Can you demonstrate me?
Yes.
What's the perfect?
See, if you want to draw cos function first, it has the frequency of 3 Hertz. Means it has the time period of 1 by 3.
1 by 3. Okay.
Which is 0.33. Something.
Yep.
No, 0.5. Yes.
3.
Yeah, seconds. That means our actual cos function starts from here, so it goes like this. The cos function goes like this. This is 0, and the whole time period is, it again starts repeating over here, right? So this is your time period Tm, which is 0.33 seconds.
Okay.
And the half of it is over here. So 0.33 divided by 2 is here. And this amplitude level is 10, and this amplitude level is -10. So we just have to draw the sample signal what you have to do, you have the sampling interval as 6, 1 by 6.
Yep.
Means which is 1 by 2 times 1 by 3. This is Tm. So it is 0.33 times 2. Means here, this is your Ts value, right?
Yep.
So you have to take the samples after every Ts time. So first sample to be taken at 0, second sample at this Ts, third sample will be at this 2 Ts, fourth sample 3 Ts, fifth sample over here somewhere. And similarly on this side minus Ts, then this I think, yeah, minus 2 Ts. So just take the samples at those instants. So first sample will be this. Second sample will be here. So like this. Third sample here, like this. Fourth sample here. No, fifth here. So the samples, now just take the red ones. So 1, this, something like, no, they are equal, no? So you can see. This is also equal in magnitude. So this is like this. So 0 at Ts, at 2 Ts, Ts value you know. So it will look something like this.
Okay.
If it is sampled at Nyquist rate. If it is not sampled at Nyquist rate, let's say if it is sampled at, it should be sampled greater than Nyquist rate, right? Lesser,
Yep.
not possible. So time will reduce. So then you might be, the samples will be every quarter. Means here, 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 here. Depends on the value of T.
Yeah.
Any doubt?
Not really. This is good. This is good. Okay. So below, wait. So this is how you draw the graph. This is
Yes.
how you draw the thing.
Yes. This is the sample signal. X
Okay.
S of
Okay.
T.
Okay.
Then we have one more, which is the quantized signal. So quantization,
Yep.
how to do and how many levels you have now? 64 levels are there, I think. No, 128 levels. Okay, it would be
Yes.
very difficult in this case to draw this graph because you have to divide this range into 128 levels. So manually doing it is very difficult. This range, which is from -10 to 10, is to be divided into, here you'll need to make 128 partitions.
Yeah.
Okay. So, and then you have to do the same thing which you are doing. Like first, this is your D1 boundary. This is your D129th boundary. The boundary will be one more than this, right?
Yeah.
Now you have to draw the remaining 127 boundaries in between, which are equally spaced. Then take their midpoints, like the mid levels, and then just simply approximate to that bound. If a signal is falling between these two boundaries, then just approximate it, to quantize it to this level, the mid level, like this. Understood?
Yep.
So if they'll ask you to draw the diagram, quantization diagram, they won't give you these many number of levels because this is not possible to draw by hand. Okay. So maximum 4 to 8 levels they'll give you. Number of levels, not more than 16, definitely. Okay. Understood?
Can you repeat that? I lost attention just now. I'm sorry. Yeah.
Okay, I was saying that they won't give you these many number of levels in exam. Maximum they'll give you 16 because manually drawing these many levels is not possible.
Yeah, it's not
right?
possible. No. Yeah.
Yeah. So if they give you 16 quantization level, then draw 17 boundaries and 16 partitions, and then just quantize the way we were doing it.
Yeah. And then you just have to, follow the things, connect, all those things. Yes. Oh, okay.
Is this okay?
Yeah, I think we will end here today. Thanks a lot. I will try to digest and then all those things, and tomorrow we do the power spectral density. Yeah. Thanks a lot.
So just revise the sampling and quantization part, and if possible, you can practice more problems on this so that it's more clear. Okay.
Yeah. Thank you.
Okay then. Bye.
Bye.